In this video, we're going to explore experiment 10, which is the gravimetric analysis of a chloride salt. So your goal in this experiment is to accurately determine the percentage of chloride in an unknown salt. And we're going to use a process called gravimetric analysis. So to show you kind of a summary of how gravimetric analysis works, basically what this is we isolate a compound and weigh a compound in a measurable form. So normally this means that we isolate it by precipitating it. We weigh that sample, which we know what it is. So in this case, we're going to take chloride out, and what we're going to be weighing is silver chloride. So we know that the chloride is in silver chloride. And then we're going to use the mass of the silver chloride to work back and determine the amount of chloride that was in the original sample. So there's kind of a general procedure for this. You have to weigh the unknown accurately. So we have to know how much stuff we start with, and then we're going to dissolve it. So we're going to get it into solution. Then we're going to precipitate the target with a known compound. So in this case, our target is the chloride. That's the percentage. We're looking for the percentage of the chloride in the unknown. And we're going to precipitate that target with silver, so with a known compound of silver. So we're going to isolate the solid silver chloride by filtration and wash to remove contaminants. We're going to then dry and weigh the product and then calculate the percentage. So the first step in calculating the percentage is to understand that when we have the isolated silver chloride, we have to be able to convert the mass of the silver chloride to the mass of the chloride. So to do that, we're going to create what's called a gravimetric factor. So if you were to have a mass of silver chloride, we can use stoichiometry to convert this to the mass of chloride that was in it originally. So what we would do is we would take the mass of silver chloride, divide it by the molecular weight of silver chloride, that's 143.32, and then this would get us to moles of silver chloride. And then from here, we can convert moles of silver chloride to moles of chloride, knowing that there's a 1-to-1 ratio. For every 1 silver, there's 1 chloride that was in it during the precipitation. And so then we can convert that 1 mole of chloride into a mass using its molecular weight of 35.45 grams. So if you take these conversion factors and summarize them, essentially if you take 35.45 and divide it by 143.32, you get the gravimetric factor, which is 0.2473. So then what we can say is, well, whatever your mass of silver chloride is, if you multiply that mass by 0.2473, this will give you the mass of chloride that was in the original sample. And if we want to calculate the percent chloride, that's going to equal the mass of chloride divided by the mass of the unknown. So we take the mass of the chloride from the gravimetric factor calculation, divide it by the total mass of the unknown that we started with, and then if we multiply that by 100, we get the percent chloride. Okay, so let's take a look at the reaction that we're going to do. So in this case, we're going to put metathesis reactions to work. So we have the chloride that's going to be dissolved in solution from the unknown. When we add silver nitrate, we're going to make silver chloride, and this is what it's going to look like. So if you were in lab, when you had your unknown and you add the silver chloride, you're going to make a white precipitate that looks just like this. So we've seen this before in metathesis reactions, but I just wanted to remind you, this is exactly what it will look like when you add the silver nitrate to that solution. Okay, so our product is going to be silver chloride, and we're going to have some NO3 minus left over in solution. Now you'll notice one thing. This is all done in the presence of nitric acid. You'll see in the procedure that we add nitric acid. So the reason why we add nitric acid, and this is kind of an important thing to keep in the back of your mind for a quiz, is we have to make sure that there's nothing else in the solution that the silver could react with. So you're probably thinking to yourself, well, what else could be in deionized water that the silver could react with? Well, there is something in water that it could react with. If you remember your chemistry, the carbon dioxide in the atmosphere can dissolve in water, forming carbonic acid. And carbonic acid can dissociate into carbonate. So in regular water, we have a little tiny bit of carbonate that's there that could also precipitate the silver. So in that case, we might get an inaccurate mass because some of our silver would react with the chloride and some of it would react with the carbonate, which would throw things off. And since we're adding an excess of silver, it's going to precipitate with anything in the solution that will that it will precipitate with. So if there was carbonate there, it would precipitate with both the chloride and the carbonate. So adding nitric acid removes any dissolved carbon dioxide because this will drive the equilibrium of the carbonate in the direction of carbonic acid and bubble out as CO2. We know that if we react nitric acid with aqueous sodium carbonate, we'll form CO2 gas. So we essentially get rid of any dissolved carbonates by adding an acid. So now there's a couple of things that we have to assume. The first thing we have to assume is that the precipitation of chloride ion is essentially quantitative. So we have to assume that the yield is 100%. And this is a pretty good assumption for this experiment because the solubility of silver chloride is extremely low. We treat that as an insoluble salt. So essentially, we can neglect any little bit of chloride that dissolves from the silver chloride because that's such a small amount that it wouldn't affect our ability to measure it, meaning it would be so little that we couldn't detect it with our balances. Oops. Okay. And the other thing we have to assume is that the quantity of chloride ion can be determined from the mass of the silver chloride. Now, this is not an assumption. This is actually what we can do. So this is where the gravimetric coefficient comes in. So if we can determine the mass of the silver chloride we precipitate using the gravimetric coefficient, we can go back and get the mass of the chloride ion that was in that solution. Okay, so here's what the experiment would look like if you were in lab. And this is a very basic experiment in terms of setup. So you're not really, you've essentially done this experiment already when you did your metathesis reactions. So the first thing you're going to do is you're going to weigh out your unknown on the analytical balance. And you're going to get a mass of 0.2918 grams. So you just take the unknown powder, you weigh it out on a piece of weigh paper, and this is how much mass you get. And then you're going to put this into 150 mils of deionized water and dissolve it. So you're going to make sure that all of the unknown dissolves into the water, and you get a completely transparent, clear aqueous solution with no solid left. Then you're going to add your 6 molar nitric acid. You add 1 mil to the solution, and then that will acidify it. And then also at this point, you're going to weigh out a piece of filter paper. And the mass that you're going to get is 1.487 grams. Now, the reason why we're weighing out the filter paper is so that in the end of the experiment, when we have the filter paper and the silver chloride, after the filtration, we can subtract away the mass of the filter paper to get the mass of the silver chloride. Okay, so to do the precipitation step, your professor would be standing in the hood, and he'd have one of these bottle dispensers. So there would be a bottle that had silver nitrate solution in it. And you would lift up on this little pipette thing here. And when you lifted it up and pushed it down, it would squirt in exactly 10 mils of 0.5 molar AgNO3. So that would be what the bottle dispenser is for. So this just allows us to weigh out an exact volume of the silver nitrate solution into your solution. Now here's where you're going to get the nice white precipitate. As soon as the silver nitrate hits the solution, you're going to see the instant that it hits a white precipitate form. So then you're going to take this back to your bench. You're going to stir it until it's completely mixed. That's just to make sure that the silver has a chance to react with all the chlorides. And then we're going to heat it up for 5 to 10 minutes with the Bunsen burner. Now the reason why we're heating it up is because when the precipitate first forms, the particles that form are actually kind of small. And if we just filtered it as is, they would clog up the filter paper and prevent the liquid from coming out. So you would basically be there for 2 hours waiting for this thing to filter. By heating it up, it causes the precipitate to essentially what we call reprecipitate, meaning it digests the precipitate and allows it to aggregate into bigger and bigger pieces. So the silver chloride kind of clusters together and forms these big clumps at the bottom of the beaker. This just makes filtration much easier. So you should know why we heat it with the Bunsen burner as a potential question on the quiz. And this is just to make the precipitate aggregates bigger so that they're easier to filter. Okay, and then what you're going to do is on your bench, you're going to set up a funnel. And in your funnel, you're going to fold a piece of filter paper into a conical shape. There's directions in the lab book if you want to see how to do it. It's not super important to know how to fold the filter paper for any particular reason, but this is what it would look like. And then into this funnel, you would pour your hot solution with the silver chloride clusters in it, and the water would go through and into your beaker, and the silver chloride would get stuck in the filter paper. So then you're going to wash your beaker with water to make sure that all of the precipitate is transferred. This is really important because we're doing a quantitative experiment today. So we want to make sure that we quantitatively transfer all of the silver chloride precipitate into the filter paper. So you have to make sure that every little speck of it gets transferred. And if you were in lab, this would actually be pretty easy if you made the clusters big enough, because you would just add a little bit of water, swirl the beaker, and pour it in, and then the precipitate would come right over. And then what we would do is we would allow the filter paper to dry for a week. So normally this experiment would take 2 weeks, because you'd have to wait until next week for it to dry. But since we're doing this as a virtual experiment, we're going to have auto-dry feature. So when you weigh the dried filter paper, you get a mass of 2.075 grams. Okay, so I just entered into the data, this data for you from the experiment that we did. So your mass of the sample was 2.2918 grams. That's what you weighed out in the very first step. And the mass of the filter paper was 1.487 grams. I apologize, and I'm going to fix this on the data sheet that's going to go up. This should be 1.4870 grams. We have to make sure that we have all of our significant figures. So you'll notice that on the data sheet that's actually posted, it'll have the correct number of significant figures. I think I just copied these down with one less significant figure. Yeah. So I have to fix those numbers to have the right number of sig figs. They should go out to the 4 decimal places, and that will be corrected when you get this. Okay, so then what you're going to do is you're going to calculate your mass of AgCl, which is going to be the mass of the filter paper and the silver chloride minus the mass of the filter paper. So that's how we're going to basically take this number minus this number, and we're going to get the mass of AgCl. Once you have the mass of AgCl, you can use your gravimetric factor, which we calculated earlier on in the presentation, to calculate the mass of chloride in the original sample. And then once you have that, we now have the mass of chloride, and we have the total mass, which is 0.2918, and you can calculate your percentage. So that's how you're going to get your percent for this experiment. The next thing we have to do is we have to analyze the data with statistics. So the whole lab, in this case, everyone in your lab, all of the groups performed this experiment, and they did it all on the same unknown. So we're going to have a whole bunch of data points that we're going to have to analyze. So the first thing you're going to do is you're going to calculate the average of your data points. And this is going to equal the sum of the data points divided by the number of points. So this is a standard average. Then when we want to calculate the deviation, what we're going to do is we're going to take the average and subtract away the data point, or vice versa. You can take the data point and subtract the average. It doesn't matter which direction you go in, because there's these bars on the outside, which tells you that you're going to take the absolute value. So whether the value comes out as a plus or the value comes out as a minus, you're going to report the value as a positive value, because this is an absolute value. All we're interested in is how different is the data point from the average. And then we can do 2 things. We can either calculate the average deviation or the standard deviation. Now, in this experiment, it doesn't ask for the average deviation, but you should know this for the quiz in case we ask it. And the standard deviation it does ask for, and you will calculate. So the average deviation is relatively simple. All you have to do is take the deviations, add them up, and divide by the total number of points. So for all the deviations you have, you're going to take the average of those deviations. The standard deviation is a little bit more complicated. You're going to take the sum of the deviations squared. So you're going to take each deviation and square it, and then you're going to and then add them up, and then you're going to divide by the total number of points minus 1. Then from that, you're going to take the square root of that whole thing, and that's going to give you the standard deviation. And then finally, you can calculate the relative deviation by taking your standard deviation, which you calculate here, and divide it by the average, which you calculate here, and then multiply that by 100. So that's going to tell you basically what percentage of your data is uncertain, right? So let's say that you have a standard deviation that's around 1, and your average is around 50. Well, that means that your data is about 2% uncertainty, because if you take 1 divided by 50, multiplied by 100, you're going to get about 2%. So that means that, relatively speaking, your standard deviation is about 2% of your total standard deviation. Now, what you want is you'd want to have a very low relative deviation for an accurate number. The lower the relative deviation is, that means that the lower your uncertainty is relative to the average. Okay, so let's take a look at some sample data just to show you what I'm talking about. So here we had a couple of students, we had 3 students do this. They got 50.25, 51.75, and 49.97. So to get the average, this is pretty simple. You take the 3 numbers, you add them up and divide by 3, and you get 50.66. So that's easy, the average. Now here's the deviation part. So what we do is we take each of those data points, 50.25, 51.75, and 49.97, and we subtract the mean away from it. And it doesn't matter which order, whether you put the mean first and the number, or the number and then the mean. It doesn't make a difference, because the absolute values, you're going to get a positive number no matter what. So whatever you get out of your calculator, you're going to report a positive number here, because these are absolute values. So these are our 3 deviations. We get 0.41, 1.09, and 0.69 when we do those subtractions. Okay, then if we want to calculate the average deviation, which is mu dev, we're going to take those 3 deviations and we're going to add them up and divide by 3. So we get an average deviation of 0.73. Now, what's a little bit more complicated, and what I wanted to show you because it's a bit more of an involved process, is calculating the standard deviation. So here, we take those deviations that we calculated and we square each one. We add those numbers up together, and then we divide it by the total number of points, which is 3, minus 1, which would give us 2 on the bottom, and then we take the square root of that fraction, and we get 0.96. So if I wanted to calculate a relative standard deviation, I would take my 0.96 divided by my average, multiply by 100, and I get 1.9%, which is relatively good for an experiment like this. And then how do we report your value and your uncertainty? So the way that you're going to report this is you have your number, which is 50.66. This is your average with the correct number of significant figures. And then we have our standard deviation. Now, what a standard deviation is this basically tells you where 66% of your data is going to lie. So if you have a bell curve and you have an average score, which is at the top of the bell, this basically says that 66% of your data, which is within the first standard deviation, is going to fall within 50.66 plus 0.96 and 50.66 minus 0.96. So the reason why we write this as 50.66 plus or minus 0.96 is because we can say, well, our average is this, but within the standard deviation, within the bell curve, most of our data is going to lie within this range of 50.66 plus 0.96 and 50.66 minus 0.96, and a majority of our data. So that's what this tells you, and that's how you're going to report it. So if you look at your data sheet, you're going to do exactly this. So here is the data from your lab mates. This is what they got. And then you're going to add yours here. So you calculate your percent composition, and you're going to add yours to this list. Don't forget to do that. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 total data points, including yours. Okay, so then what you're going to do is you're going to take the average, and you have to show your calculations. So you have to write down what you're doing, how you're setting it up, and then write down what your average is. The standard deviation, you're going to use the calculation above, and you're going to show all your work, how you get the standard deviation. So somewhere down here, you can calculate your deviations. And then over here, you can set your standard deviation equation up, or however you want to do it. Just make sure it's clear to your instructor what you're doing. And then you're going to write your standard deviation. And then here, you're going to write your relative standard deviation following the equation above. And then the last thing you're going to write is the reported percent chloride, which is going to be your average plus or minus your standard deviation. Now, there is also a question here that says, do any of your results differ from the mean by more than 2 standard deviations? So what this is asking you is, let's say that your standard deviation was what we had on the previous page. Let's say that it was 50.66 plus or minus 0.96. Well, if you were to take 2 standard deviations, you would add 50.66 plus 2 times 0.96, and 50.66 minus 2 times 0.96. And that would give you a range. Now, within that range, about 99% of the data would fall within that 2 standard deviation range. So what we're basically asking you is, did anybody screw this experiment up? Meaning, if these are all the data points, are any of the data points statistically so different from the average based on all the rest of the data points that it clearly is not a right answer, that the group made a mistake? So that's going to be your job. You're going to add your standard deviation times 2, subtract your standard deviation times 2, figure out what the range is, and see if any of the data points in this list, including yours, fall outside. And the answer will either be yes or no. And you might want to you should put down if the answer is yes, which data point it is. Okay? So that is experiment 10. It's a nice, short, simple experiment. The calculations are very straightforward, so I think you guys will be able to do this pretty easily. If you have any questions, you can contact your instructors, and this will be due at your normally scheduled lab time for experiment 10. At the end of it, there'll be an upload your work thing. Now, also, you're going to get this data sheet in that upload and the link to this video.